Hey, what's up, guys? This is Chung here. So today, let's take a look at LeetCode 1830, minimum number of operations to make string sorted. I mean, this is a very, very interesting problem, and it's also like kind of hard, because you're given like a string, right? And you're asked to perform the following operation on an S until you get a sorted thing. You get a sorted string. And you just need to return the number of operations needed to make the string sorted. And since the answer can be too large, do a modular, right? So then what is this operation doing? So first, we find the largest index, basically the last index, where the current letter is smaller than the previous one, right? And then we find the another largest index, right? I mean the where the j is greater than I, and all the letters between I and j are smaller than this kind of s I minus one, and then we swap this I minus one and j, and then we reverse the remaining from I. Seems pretty annoying, right? So what it's doing? Let's try to write a simple. Okay, let's try to give an example here. We have, I'm just giving this B, C, D, H, B, C, D, E, and M. So if we have this string here, right? So what is I here? So the I that the last I who is smaller than the previous one, which is what? Which is B, right? Which is this one. This is the I. Because all the remainings, they're all bigger than the previous one. Only this B is smaller than this I minus one. This is I minus one, right? So we find I, and then we need to find the j. So what is j? J is the ones after I, right? Who's like who's all the letters between I and j are smaller than this I and the I minus one, which is h, right? So what we have? We have j. This is j, right? And then what we're doing? We're swapping this I minus one j. So we have B, C, D, E, B, C, D, H, and M, right? And after this one, what we do, we reverse, start everything from I, which is B, C, D, E, this is I, right? M, H, D, C, and B. So this is what we're getting, right? Since we're always reversing like a letter which is smaller, right? Then this I minus one, we're definitely making this string smaller than the previous one, right? But what is this operation actually doing? So actually, if you watch closely, or if you kind of like insightful enough on the permutation, actually this one, this one is a previous permutation of this one. Basically, if you're trying to get the next permutation from this one, you will get this one. Because if you guys recall how there is like a problem on LeetCode asking you to do the next permutation, right? So how do we get the next permutation? It's exactly the opposite way as this operation, where we find the last element, we find the last index whose value whose value is smaller than the next one, which is in this case is this one, right? I mean, this is the index. And then we do what? And then we also do another search from the end, trying to find the trying to find the first, right, the first element who is greater than the current e, which is in this case is what is it's h, right? And then we do what? We swap this two, right? We swap these two. Now this one becomes to h, this one's become to e, and then we do another reverse, right? Another reverse from here to here, which is exactly back to the state, to the previous, to this one, right? H, B, C, D, E, M. So this one, this one is kind of obvious, right? Because first we find that the last one that we might be able to make this one bigger, right? Because we know, okay, so for this one we are definitely can make this one bigger, right? But in terms of which letter we're trying to change this one to, we're going to try to find it, change to the one that find the number from the last, right? From the last to here, so that we can make this one bigger. But after this one, since we find that we want to make the permutation, it means that we want to make this one move to the last, so that we can get, so after this one we can get the smallest, right? We can get the smallest permutation after this h here. That's how we find the next permutation. So basically, when we find the next permutations, since we know everything starting from I is in the descending order, right? Basically, we're finding the first, the smallest letter who is greater than the current one, right? Then we're just like replace that one to here, and then like I said, after that, since we're going to make the remaining parts to the smallest number, since the after swap, this part is also like in the descending order. We simply just need to reverse the remaining, right, into the so that it can be into an ascending order, which means that it's going to be a smallest number, smallest string, right? Anyway, so that's a little bit about the permutation. So basically, now the problem comes down to given like a string, right? How many permutations before the current string, right? Until it reached the assorted string, right? So if we take a look at CBA here, right? So we have if we have a CBA, right? So from CBA we have CAB, right? If we just write down all the simulation here, and then we have BCA, then we have BAC, ACB, and then ABC. As you guys can see, this is like the steps for the permutation. So from ABC, the next permutation for ABC is ACB, and the next one is BCA, BAC, BCA, CAB, and CBA. This is the given string, right? And the answer is 5, which means that there are like 5 permutations before S, who is smaller than S, right? So now the problem converts to, we need to find the total permutation of string, right, who is smaller than the current S. Okay, and to calculate that, right, we need a little bit of math knowledge. So, if we have some like string here, right, starting from here, how can we know how many strings are smaller than the current string? Let's say for example we have the first letter is C, right, and then we have some letters here, and then we have A, and then we have another 2B, something like this. So obviously, for at C here, how many options we have? We have 2 options, right? We can just put any letters who is smaller than C to here. In this case, is A and B. Right. So basically, if we replace this one to either A or B, anything after A, anything So of here will be all the combinations or all the permutations on the in the remaining parts can be they're all smaller than the current one, right? And the second option is that we can just simply leave C here. We don't change it, right? And then we're trying to make the remaining part a smaller number, right? Actually, no, as you guys can see now, this one is a sub problem, right? So we can apply the same logic on this substring here, right? Which means that for this one we can just check what's the number of this one here, what's the letter for this one, and then to be able to make like the smaller string for this substring here, we do the same thing, right? We check if the remaining part, if this remaining part has any letter smaller than the current one. If it is, then we simply just move all this letter to here, and then the remaining part, all the permutations of the remaining parts are smaller than this substring here, right? So then, how can we calculate the permutations? Actually, this is kind of like a combinatoric problem, with like duplicate number, right? So let's say we have C here, right? So assuming we either place A or B here, how many remaining letters we have? We have 1, 2, 3, 4, 5, 6, 7. So we have 7. So the total permutation of this one is what? 7 factorial, right? That's the total permutation, right? And so the total is 7, right? 7 factorial. And then let's say, for example, let's say we have, let's say we have 2 E's here, right? We have 2E, and this one is also C. How about that? So we have E, E, A, C, B, B. This one is also a E here. So basically, this one is the permutation with duplicate numbers. So if you guys know this kind of concept, basically, the total permutations with duplicate is what equals to the total number of factorial divided by each count by the factorial of each count of distinct numbers. So in this case, let's say we have this one E, A, C, B, B, E, right? So the total permutation for this one is going to be what? So we have 3E, right? That's why we have 3 factorial, right? Times we have two B in this case, right? So we have 2 factorials, and then we have 1A and 1C, right? That's why we have 1 times 1 times 1. That's the total. Basically, that's the total permutation for this one. But of course, since we're going to like swap the number, the letter who is smaller than the current one, we have to update this number accordingly, right? Basically, let's say after swapping, let's say if we swap these two numbers, right? Because A and B, we need to swap all the A and B with C. So after swapping, so what do we have? 7 is the same, right? But now we have 3 E's, right? And then we have 2B in this case, right? But now for A and C, we don't have A anymore, but instead we have 2C. That's why, instead of this one, we're gonna change this one to 2 factorial, right? And that's basically our logic, right? So basically for each of the at each of the states here, right, we're going to check, right, basically how many like letters on the right side is smaller than the current one. If it is, then we simply swap each one of the letters with the current one, and then we're gonna calculate the permutation accordingly, right? And then like I said, since for the case, if we don't change this one, leave it as C, and then we're gonna use the same logic to recursively to calculate the substrings, right? That's why when we do the loop here, we can loop from the last. We can do a reversing loop because we want to know the total count, right, on the right side. That's why we can start from the end. So that's the basic idea here. And the last thing is that to calculate this thing here, if you look at the constraints here, the length could be up to 3,000. So if you're trying to calculate 3,000 factorial, this one is going to be too big, right? And it will overflow in Python if you use like a Python integer, right? Because that the digits which is just way too big. So that's why there's like this technique called inverse factorial. This one is often used in the competitive programming. Basically the inverse factorial with modular, because it says that since the number will be too big, we'll be using the modular along the way, right? But for these things, we cannot do everything. We cannot do like a factorial of this one and then we do a modular at the end, right? So we have to do the modular along the way. And a technique of doing that is to do an inverse factorial, and then we'll do the inverse factorial to handle this kind of thing. So which means that when we calculate the factorial, for like 3,000, from 1 to 3,000, at each of the numbers, we're always going to do the modular after that, so that we are making sure the number will not be exceeding, will not overflow. So if you guys want to know a little bit more about what was the logic, what was the theorem behind it, you can just look it up online. There are a bunch of other like articles talking about that. So yep, I think we can start coding. I'll try to explain a little bit more. So starting with, we have like n, right? And then we have a modular starting from doing the modular here. And then I'm going to define like two arrays. One is for the factorial, starting from 0. And then the other one is for the inverse factorial. Okay. So at the beginning, the factorial is the 0 equals to 1, and then the inverse factorial, we use a power. We use the power function to calculate that. So it's going to be starting from 1, and then the power is like mod -2, and then we have a mod. For this one, just remember that that's the way we're calculating the inverse factorial. And then for I in range of 1 to n, right? So first we have factorial I equals to the I times factorial, right? Then I minus 1, right? And then we do a modular, right? And then we use the new factorial to calculate the inverse factorial, similar as what as above. So we have this one. Now the base is factorial I, right? And the power is still mod 2, and then -2 and mod. Okay. So now we have this kind of factorial, and it's an inverse factorial for each number here. So that when we calculate this like 7 power, like the very big number, let's say we have a like huge number of like n, right? Let's say we have n divided by k, right? Both this one is very big. So what we can do, we can simply use this when we try to do this k divided by k factorial, we can simply do a n factorial times this inverse factorial of k. So that's basically how this thing inverse factorial works. Of course, we all do this modular, right? Okay, so now I'm going to create like counts, you know, to count the the frequency, the letters so far, right? Since we're going to loop from the end, right? And then so we have the answer equal to 0. So for C in S -1, okay. So for this one, so first I'm going to convert this one into an index, into a like integer value. So we do a ordinal of C minus ord A, right? So first we increase the counts, right, of this index by 1. Remember, so because we need to use this kind of like counts to do our permutation calculation, right? And the next thing is that, you know, basically, you know, this is the current one, right? So this is the current. So basically, we're at this location, and we want to check, right? We want to know what are the letters on my right side, which is smaller than the current one, right? That's why, you know, we can simply do a what? We have the index, right? So anything that's smaller than this index is smaller than the current one. So we can simply do a for I in range of num. Okay, this is the index, right? And then if the count I is greater than 0, right? This means that, you know, okay, so we have some like numbers, letters on the right side, which means that the ones we have already looped through, which is because the count is greater than 0, and it will not include the current one because, you know, we are not using this number. We're using the value smaller than the number. So this one means that, you know, there is a letter, right, on the right side who is smaller than the current one, right? So first, you know, we're going to swap, right? So we swap. Now we swap. Okay. So after swapping, you know, we have what? We have current. This smaller one. This one will be smaller. Will be decreased by 1 because this one. Let's say if we have this one is C, right? And we have 2 A's here. Okay. After swapping, you know, this letter, the count for the smaller letters will be decreased by 1 because we're gonna use this count to calculate the permutation later on. And later on, you know, in the end, we're gonna add it back so that, you know, it will not affect other swaps, right? And also, since, you know, if you have 2 letters, let's say this count is greater than 1, you know, we're swapping this, either one of them are the same. That's why we only gonna calculate those numbers, those same letter once. Okay, so after swappings, you know, we're gonna do this kind of permutation, you know. Actually, it's like permutations or like operations, right? Basically, how many operations we have. So at the beginning, you know, we have this kind of total factorial, which is the factorial of the total numbers, total letters. So for that, okay, so let's just create like another variable called total, right? Basically, every time I increase total in the end, so which means that, you know, the current total are the numbers, right, on my right side, right? That's why, you know, at the beginning, you know, the total permutation is like factorial of the total, right? And then the divider part, right? This part. So we have to we can simply loop through the counts, right? We loop through the counts, and if there's anything in the counts, then that's the That's the we're gonna add it to here, right? We're gonna use the inverse one. So which for j in range of 26, right? So we have 26 letters in total. If the counts of j is greater than 0, right? It means that we're gonna divide it, that factorial, right? So when we divide, like I said, we're gonna use like a trick of the inverse, right? So ops is gonna be the ops times the inverse factorial, right? And then gonna do a counts of j, okay? And then we always do a modular, right? To make sure it will not overflow. Basically, these ops are the new strings or the permutations who is smaller than the current string, right? That's why we're gonna add this one to the final answer, right? And then in the end, we're also gonna do a like modular of the answer, right? And then in the end, we can just return the answer. So yeah, that's it, right? I mean, so here we find this is the total, right? Total permutation, right? Total factorial. Here we find the count for each letter, right? And the count for each letter are these parts. And then we use the inverse factorial to calculate that with the modular, right? So yeah, I think that's it, right? So if I run the code, counts, right? Click accept it, submit. Yeah, so pass, right? I mean, so for this, the time complexity, right? So the time complexity, we have n here, right? So we have n, and so for each letter, we have n here, and then for this one, this is like in the range of 26, right? So we have n times 26, and then maybe we have another 26 here, right? So there's another 26 in total. Yeah, so that's going to be the basic time complexity for this. And yeah, I mean, assuming this power will not take too much time, right? Cool. So just to recap, right? I mean, so the nature for this problem is that we need to find how many strings, how many permutations of the current string is smaller is smaller than the current string, right? And then we simply need to find a way to do the calculation, So the way we're calculating is that at each of the location here, we simply need to find like how many letters on the right side who is smaller. If there's any letter on the right side which is smaller than the current letter. If it is, then we simply swap, right? And after swap, we can use the updated counts to calculate the total permutation with duplicate, right? And then we accumulate that into the answer, because that's going to be all the permutations that who is smaller than the current one, right? And then, like I said, and for the case that we didn't change, we didn't swap, right? That's why we have this for loop here. So let's say, for example, this is C, and then we have A and B here, right? So inside the for loops, inside for loop here, we're swapping C with A, either A or B, right? And then for the case that we didn't swap, let's say we keep the C here, and then we're trying to make this one smaller. For that one, that's why we need that's what this outer for loop is for, right? Basically, we're trying to at each of the index here, right? We're trying to calculate the calculate the smaller one. That's why, we're covering this second scenario, which we're not swapping this one. Yeah, I think that's it. I know this one is pretty tough, and especially for this kind of inverse factorial part. But yeah, hope you guys like this video, and thank you for watching it, guys. Stay tuned. See you guys soon. Bye bye.